Hello students, today we are going to study the defects in solid state and would be focusing on stoichiometric defects in this video. Let us start. Defects. The arrangement of atoms or molecules in most crystalline materials is not perfect. The regular patterns are interrupted by crystallographic defects. These are broadly divided into two categories: point defects and line defects. Point defects. When the deviation or irregularities exist from ideal arrangement around a point or an atom in a crystalline substance, the defect is called as the point defect. Line defects. When the deviation from the ideal arrangement exists in the entire row of lattice points, the defect is called as line defects. Our syllabus have point defects in it, so we will be studying that only. There are three types of point defects. First, stoichiometric defects. Second, impurity defects. And third, non-stoichiometric defects. We will be studying stoichiometric defects in this video. Stoichiometric defects. If the imperfections in the crystal are such that the ratio between the cations and anions remains the same as represented by the molecular formula, the defect is called stoichiometric defect. These defects are also called as thermodynamic defect or intrinsic defect. In non-ionic compounds, there are two types of stoichiometric defects. First, vacancy defects. Second, interstitial defect. Let us see the vacancy defect first. When some of the lattices are vacant at certain sites, the crystal is said to have vacancy defect. These are generally shown by non-ionic solids. As you can see it in the picture, the perfect crystal have all the lattice sites, all the atoms intact, whereas in vacancy point defect, one of the atom is missing. Let us understand it through a video.
In a crystalline solid, some of the lattice sites are vacant. The crystal is said to have vacancy defect. This generally arises due to the absorption of heat from the surroundings, which results in the decrease in the density of the substance.
This results in decrease in the density of the substance. Now moving ahead with the interstitial defect. When some constituent particles occupy an interstitial site, the crystal is said to have interstitial defect. This is generally shown by non-ionic solids. You can see it in the picture also. The constituent particle at one particular site is missing, and this is the interstitial defect. Let us understand it by one video.
Interstitial defect is caused when some of the constituent particles, can be atoms, molecules or ions, are present in the vacant spaces in the crystal structure. These vacant spaces are known as interstitial sites, and the particles present in these vacancies are known as interstitials. As the number of particles within the crystal increases, the density of a substance increases.
As the number of particles increases, the density of substance also increases. Ionic solids generally show two types of stoichiometric defects: Shortkey defect and Frankel defect. Let us see them one by one. Shortkey defect. This defect was discovered by German scientist Shortkey in 1930. It arises if some of the atoms or ions are missing from their normal lattice sites. The lattice sites which are unoccupied are called lattice vacancies or holes. Here, in this type of defect, equal number of anions and cations are missing from lattice sites, in order to maintain the electrical neutrality. Let us see it by this video.
Shortkey defect is similar to vacancy defects. This type of defect is created when equal number of positive ion and negative ions are missing from their lattice sides, so that electrical neutrality is maintained. Here, mass decreases while volume remains the same. Presence of a large number of Shortkey defect site lowers the density of the solid.
Shortkey defect is shown by ionic compounds which have high coordination number and which have a small difference in the sizes of cations and anions. Few examples of ionic compounds exhibiting Shortkey defect are sodium chloride, potassium chloride, potassium bromide, silver bromide, and cesium chloride. There are some effects of Shortkey defect. The density of the solid decreases. It conducts electricity to a small extent and it lowers the stability of crystal. Let us see the Frankel defect. This defect was discovered by a Russian scientist Frankel in 1926. It arises when an ion is missing from its normal position, causing a vacancy or a hole, and occupies an interstitial site between the lattice points. The smaller ion is dislocated from its original site to an interstitial site, creating a vacancy defect at its original site and an interstitial defect at its new location, also known as dislocation defect. It is shown by ionic solids. Let us see it by this video.
If in an ionic solid, a smaller ion, generally cations, goes missing from their lattice site and occupies the interstitial site such that electrical neutrality as well as the stoichiometry of the compound are maintained, this type of dislocation is called Frankel defect and also called as dislocation defect. This defect is a combination of vacancy defect and interstitial defect. It is a vacancy defect at its original site and an interstitial defect at its new location.
Now, let us see that this Frankel defect is shown by ionic compounds which have low coordination number, a large difference in size between cations and anions. Frankel defects are found in silver halide due to the small size of silver ion and in zinc sulfide due to small size of zinc ion. In pure alkali halides, Frankel defects are not observed because the ions are bigger than the voids. There are some effects of Frankel defect. The density remains same. It increases the dielectric constant and conducts electricity to a small extent. We observe that vacancies or holes are present in crystals with Shortkey as well as Frankel defect, but the former leads to decrease in the overall density of the substance, but the latter does not. Thank you.